Hello one and all to the fifth lesson on Year 13 Differentiation for Edexcel's A-Level Maths course. So this marks the fifth lesson out of 10 and we're going to have a look at something called the quotient rule now. So we can actually derive a proof and show the quotient rule from the product rule from the previous lesson 9.4. I'll also link you to another more formal proof in both the video description, and I'll mention later on as well how it can be proved in a different way, this quotient rule, which also is very powerful and one of the key results we need to know for the course. So before we come on to that, I'll just want to throw back to a couple of previous topics for revision purposes, in other words, a warm-up. So here we go. Two questions. The first is mechanics involving a pulley, and the second one is about the equation of a circle. So let's see how much you remembered from year 12, and pause the video now and attempt these on your own, then press play when you're ready to see the solutions and I'll guide you through, and hopefully your solutions may well match mine. Okay, so assuming you've done that, let's have a look together at the answer to warm-up question 1. So question 1, we have obviously a pulley, and we've got two particles here, particles P and Q, which have a mass of 0.5 and m kilograms respectively. Importantly as well, it says that m is less than 0.5. So what this means is this particle here is smaller in mass than this one. So in other words, this one's heavier, and so the direction of motion is going to be down here. So this system will accelerate down at this side, and it will be accelerating upwards at this side. The magnitude of the acceleration will be the same because both particles are connected by an inextensible string. So let's read on. Initially, P is 3.15 meters above horizontal ground. We've nicely given that information to us in the diagram. And the particles are released from rest with the string taut, which means tight, and hanging parts of the string vertical, as shown above. So we're talking about vertical motion with constant acceleration. After P has been descending for 1.5 seconds, it strikes the ground. Show the acceleration of P as it descends is 2.8 meters per second squared. We know it's going to be that because the acceleration is constant, and we know the acceleration is constant because this system has an inextensible string, both are interconnected, and the tension therefore is constant. Acceleration due to gravity is constant, therefore the net acceleration will be constant. In other words, this is a SUVAT problem. S-U-V-A-T. So let's just fill in what we know. So relative to particle P, by the time it gets to the ground, the displacement S is going to be 3.15. So I'll just highlight how we've got that. Basically it says P is 3.15 meters above ground, so that's just our S like so. As well, it says here that the system is released from rest. So where does it say this? Yes, it says there from rest. Couldn't quite find it there. Particles are released from rest. So that is another way of saying the initial velocity is 0. So we know u is 0. So after it descends for 1.5 seconds, it strikes the ground. We therefore know the time elapsed for that motion to take place is 1.5 seconds. So we can fill this bit in. And the question part A is asking us is about the acceleration. So the thing we actually want to know is the acceleration. So A, I'm going to put as a question mark. The final velocity we don't know, we're not asked for, we don't care about simply, so we're going to cross this one off. So we need one of these SUVAT formulas that doesn't involve V at all. And if you have a quick brain scan or have a look for your notes, you should hopefully find that the formula we're wanting is the good old S equals UT plus half AT squared. Once you've identified the correct formula to use, it's just a case of plugging in the correct values and trusting that it will drop out accordingly. So S is 3.15, U is 0, so if you really want to, you could say 0 multiplied by 1.5, but I'm hoping you'd know that this is going to be 0 anyway, so this can be ignored. I'll just include it for full working purposes. Then plus a half times A, which is what we're trying to find, multiplied by the time squared, which is 1.5 squared. So all we've done here, like I've said before, is just plugging in the numbers. Plugged in the S is 3.15, the initial velocity is 0, the time elapsed is 1.5, and the acceleration, of course, is the very thing we're trying to find. So if we simplify this down now, 3.15 is obviously just 3.15. This stuff here is worth nothing. In other words, can be ignored entirely. And then a half multiplied by 1.5 squared, we can calculate using, well, a calculator. So 1/2 times 1.5 squared. This is going to give us a value of, let's see, 9/8. So 3.15 equals 9/8 multiplied by a. Therefore, the acceleration is going to be 3.15 divided by 9/8, or multiplied by 8/9, whichever you prefer. So let's just work this out now. So divide this, I've got 9/8, sorry, so 3.15 divided by the answer of 9/8 gives me indeed 2.8 meters per second squared, which is exactly what we were wanting to prove. So we've now done part A. Very sort of slanted lines there, never mind. Part A is done. Now let's consider part B. We need to find the tension of the string as P descends. So P is going down. Tension will always act to resist motion and always acts away from the particle. So the tension here relative to P will act upwards, and the tension relative to Q also will act upwards and away from it. So just considering P, the net force must be going down because P is accelerating downwards. So if we apply the principle of F equals ma, Newton's second, then the overall force going down on particle P, we've got its weight. Weight is mass times gravitational field strength, so going downwards on P is 0.5 g. So therefore the net force downwards acting on P is 0.5 g minus t, and that will equal its mass, which is 0.5, multiplied by the acceleration, which we worked out from part A, is 2.8. Therefore, with a simple rearrangement, t will be 0.5 g minus 0.5 times 2.8. Half of 2.8 is 1.4. If you calculate this now, half of g is 4.9 minus 1.4. That's going to give us 3.5, and of course, it's going to be newtons. So part A, 2.8 meters per second. Part B, 3.5 newtons. Let's have a look at question 2 about that circle. Question 2, we've got this circle with this equation, x squared plus 3x plus y squared plus 6y equals 3x minus 2y minus 7. Find the centre and the radius of this particular circle. The first thing I'd spot is that I've got a positive 3x on one side and a positive 3x on the other. I can therefore just cancel these off both sides by subtracting 3x from both sides. Now, the equation of a circle, what I want to aim for is x minus a squared plus y minus b squared equals r squared. That's a circle, centre A, B, and the radius r. That's going back to year 12. You may have forgotten that, hopefully not, but forgetting stuff isn't against the law, as long as you remember it now. In fact, if you didn't, it's still against the law, but my suggestion is to remember it now. So, we need to rearrange this so that the other side is equal to r squared. But before we do that, let's just get it all onto the left-hand side and all equal to 0. We need to, as you can see, complete the square, isolate the x parts and the y parts into 1. So here, I can clear this minus 2y and this minus 7 by both adding 2y and 7 to both sides. So over here, if I add 2y and 7 to both sides, this will give me x squared plus y squared. 6y plus another 2y will leave me with 8y. Then plus 7 equals 0. So completing the square on the x squared things, I'm going to consider the x squared as x squared plus 0x. So you'll see why in a minute. So I'm just going to call this x plus 0 squared. Over here, y squared plus 8y, we can complete the square on this. So essentially, instead of y squared, we put a y in the brackets. We half the coefficient of the y, so half of 8 is 4. We square all of that and subtract away the 4 squared, so we subtract away 16. So this here, in completed square form, becomes this. And then we don't forget the plus 7, because that would be rude. Plus 7 equals 0. Next line, leave the x plus 0 squared in its brackets. We've got plus y plus 4 squared. Minus 16 plus 7 is minus 9 equals 0. Therefore, final step, x plus 0 squared. You could just write x squared if you want to, by the way, as long as you're comfortable with that. Means the x coordinate of the centre of the circle is 0. And then we've got the y plus 4 squared. Add 9 to both sides equals 9. And so we've got it in the correct form. Therefore, we can answer the question as we need. So the centre is going to be this value here if it's sign switched. Minus a becomes plus a and so on. Plus 0 becomes minus 0. In other words, still 0. And over here, plus 4, the y coordinate is minus 4. Like so. That's the centre of the circle. Its radius is 9. Sorry, radius squared is 9. So therefore, radius is the root of 9, which is 3. So that's part A completed. Next, for part B, we're asked to find the points of intersection of the circle and the y-axis. When the circle, or any curve for that matter, crosses the y-axis, the key thing to note there is when we cross the y-axis, the value of x is 0. So without saying it, the thing we need to do is to sub in that x equals 0. And if we do that, this equation here becomes 0 plus 0 squared plus y plus 4 squared equals 9. In other words, y plus 4 squared equals 9. You could have got to that stage in one step, I suppose. Square root both sides. Y plus 4 equals the square root of 9, which is 3. And please do remember, when we square root, to consider plus or minus. Common mistake. So therefore, y equals either minus 3 minus 4, which is minus 7, or if y is positive 3, y would be plus 3 minus 4, which is minus 1. So therefore, the points of intersection, when it crosses the y-axis, x is 0, like we've said. So we've either got 0 and minus 1, and also x could be 0 and y could be minus 7. So those are the 2 points where the circle intersects the y-axis. Finally, part C, show that the circle does not intersect the x-axis. Well, if it were to intersect the x-axis, the value of y would be 0. So here we can just sub in that y is equal to 0, and let's see what we obtain. So if y is 0, we then get that x plus 0 squared, or just x squared if you want. If y is 0, this becomes just simply 4 squared equals 9. Therefore, subtracting 4 squared from both sides, we want x squared to be equal to 9 minus the 4 squared. So 9 minus 16 is minus 7. So therefore, x would have to be plus or minus the square root of negative 7. And unless you're doing further maths, in fact, even if you were, this means it's got no real solutions. So therefore, we just say, therefore, no real solutions. So in other words, we need to conclude in context, i.e., circle does not intersect the x-axis. So as long as you conclude in context and relate it back to what the question is asking, we're good as gold. So hopefully that's got your brain kicked into gear. So now let's move on together and have a look at this thing called the quotient rule. So, the quotient rule, what is it? Well, we can prove it and then we can demonstrate what it means after the fact. So we can use the chain rule and the product rule to arrive at a formula for differentiation of quotient of functions. So quotient of functions is when you've got one function divided by another. So a compound function, and this can be differentiated with a formula we're going to show here, called the quotient rule. So, step 1, this is how to prove it using the product rule, which hopefully you're a bit more familiar with by now. So, set y to be 1 over a function v, where v itself is a function of x. So if you just write y equals 1 over v as v to the power minus 1, so writing the function in index form and using the chain rule, what we can show that if y is 1 over v, then dy by dx is minus 1 over v squared times dv by dx. So if we apply the chain rule to this, then obviously I've said that y can be written as v minus 1, and by the chain rule, dy by dx, normally we'd be saying dy by du times du by dx, but I'm calling this function here v, because it's 1 over v. So replacing the u with a v, dy by dx is dy by dv times dv by dx. Now differentiating y with respect to v, y is v minus 1. So if I differentiate this, the power comes to the front, and then I take one off the power. So dy by dv will be minus 1v to the power minus 2. And dv by dx, I can leave in that exact form, just leave it as dv by dx. So writing this now as a fraction, minus 1v to the minus 2, I can write as minus 1 all over v squared, and leave the dv by dx as it is. So therefore we've shown if y is 1 over v, then dy by dx is minus 1 over v squared multiplied by whatever the dv over dx is. So just cling on to that, make a note somewhere. Hope that's convinced you that if I just set y to be v to the minus 1, then the derivative of that is minus 1 over v squared dv by dx. We're going to use this result later in our proof. So moving on to the second step. So step 2. Now reset y. I could have called it a different variable, I suppose, but people tend to be more familiar with y. So scrub that, put your note to one side, what we said before. Now think of a new y, and now think of this y as being a quotient of two other functions, so that y is a function u divided by the function v we mentioned in step 1. So again, rewriting y as y equals u times 1 over v, remember 1 over v from step 1, and applying the product rule, we can see that u over v dashed is u times 1 over v dashed plus u dashed times 1 over v. So that's just applying the chain rule. So the chain rule, sorry, the product rule. The product rule, uv dashed, remember, is u v dashed and then plus u dashed v. So it's the same idea if you're wondering, but the only difference here is instead of having v as one of our products, our product now is 1 over v. So hopefully you can see here it's the same thing, just with the v dashed replaced with 1 over v dashed. Same thing entirely. So based on this, u over v dashed is u times 1 over v dashed plus u dashed times 1 over v. But we now know from step 1 what 1 over v dashed is. So moving forward with this, from step 1, like I say, the derivative of 1 over v dashed is minus 1 over v squared times dv by dx. So we can plug this expression for the derivative of 1 over v dashed in place of it here. So piecing this together essentially now gives you the quotient rule. So if y is u over v, which is u times 1 over v, by the chain rule, dy by dx, like we've said here, is this expression. But 1 over v dashed, we've seen from step 1, is the same as minus 1 over v squared dv by dx, like we've said here. So we've got u multiplied by this expression plus 1 over v multiplied by du by dx. What we can aim for here is a common denominator on the bottom. Get the v squared on the bottom here. So this has a denominator with v squared on it. This is just 1v. So my next step, I'm going to multiply the top and bottom of this expression by v. So 1 over v then becomes v over v squared, multiplying top and bottom by v to keep it equivalent. So we now arrive at this. We can now factorize out this 1 over v squared. So factorizing out 1 over v squared, this gives me v multiplied by du by dx minus u multiplied by dv by dx. So we've got it here. Therefore, this is in red, this is the quotient rule. If y is u over v, where u and v are functions of x, dy by dx is v du by dx minus u dv over dx, all divided by v squared. And as we've seen from before, using the product rule, there are different ways of writing the same thing. So what are these different ways of writing it? Well, in dy by dx notation, we've got this as I proved just in the other slide. In function notation, using y equals u of x and v of x, we've got this here. Or the shorthand, if we've got u over v dashed, we've got v u dashed minus u v dashed all over v squared. This is the one I'll be using in this video, just because that's my preference. If these other two read easier to you and make more sense, use these expressions instead. All these three are equivalent, but I'm going to plump for this one here, because in my silly brain, u over v dashed I think of as vuv over v squared. And that's ridiculous, but it works for me. Vuv over v squared, remembering we're minusing in the middle, and the last things are what we're taking the derivative of. Now let's differentiate some quotients, shall we? So, given that y is 3x over 10x plus 1, find dy by dx. This is a very simple first example, I'm sad to say. They will be harder than this in the year 13 test, but we'll get to that in a second. Question 3 on the worked example is just a beast. So anyway, first of all, question 1, find dy by dx. So I'll just remind you what the quotient rule is, because it's quite new. It's this thing here. U is a top function, v is a bottom. So simple as this. Just set u to be 3x and v to be 10x plus 1. So I'm going to write this down first of all. Whoops, don't want it in red. U is 3x and v is 10x plus 1. We then need to differentiate both of these. So dead easy. U dashed is going to be 3. If differentiate 10x plus 1, I'm just going to be left with 10. So like I said, u is 3x, v 10x plus 1, and then the derivatives of both, we've got u dashed is 3 and v dashed equals 10. We just simply plug this in to our formula now to find u over v dashed. So therefore, dy by dx is going to be v, again that's in a damn red colour, silly, 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 change it to a standard black. There we go. So we've got that u over v dashed, in other words our dy by dx we're trying to find, is the function v times u dashed. So v is 10x plus 1 multiplied by u dashed, which is 3, minus the function u, which is 3x, multiplied by v dashed, which is 10, all over v squared. V was 10x plus 1, so that's 10x plus 1 all squared. So u dashed is 3, v dashed is 10, if you wonder where the numbers are coming from. The v was 10x plus 1, hence we put 10x plus 1 there, and u, of course, is 3x all over v squared, where v is 10x plus 1. If you're wondering about what form to leave it in, normally the examiner will be clear in terms of how to write it, so we can actually leave this all over 10x plus 1 squared. We just need to simplify this top. So multiplying this by 3 gives us 30x plus 3, but obviously minus 3x times 10 is minus 30x all over 10x plus 1 all squared, and obviously you can see now the top's going to simplify very easily indeed. So therefore, dy by dx, 30x minus another 30x, quite clearly will cancel. That'll just leave us with 3 over 10x plus 1 all squared. And that's the first one done. Simple as. Know the formula, plug in your values, but like I've pre-warned you, it can get a bit trickier than that. That's the basics. Let's take it up a slight notch. Look at worked example 2 now. So now we have that y equals cos of x over e to the 3x, where x is in between minus pi over 2 and pi over 2. It has a stationary point at w. So find the coordinates of w, giving your answer correct to 3 significant figures. Once again, just a reminder, this is what we're dealing with to find the derivative function. So let's just write in what we have in the same way as we did for worked example 1. So our u, the top function, is cos x. The bottom function v is e to the 3x. So let's just write these in. At the top, u is cos x, and v is e to the 3x. Like worked example 1, we now differentiate both. U dashed, cos differentiates to minus sine, we have to remember that one. And if we differentiate e to the 3x, this gives us 3 e to the 3x. The constant comes to the front. If this is a bit confusing to you, maybe just have a look at the videos 9.1 and 9.2 when we looked at differentiating exponential functions. So cos x is u, v is u dashed is minus sine x, v is e to the 3x, and finally we worked out that v dashed is 3e to the 3x. So if we have a stationary point, this is saying that dy by dx is 0 at w. So that's the key insight we need to make. Stationary point means the gradient is 0, so dy by dx is 0 at this point w. So what we do now is we work out dy by dx and set it equal to 0, and that'll give us the coordinates of this w point. So it's vuv over v squared, in my silly way of remembering it. So v is e to the 3x, so I'm going to have e to the 3x multiplied by u dashed, which is minus sine x, minus away function u, which is cos x, multiplied by v dashed, which is 3e to the 3x. So a bit of colour doesn't hurt things to go along nicely. So cos x, so v, was e to the 3x, u dashed minus sine x, minus u, which is cos x, multiplied by v dashed, which is 3e to the 3x. And all of that is going to be divided by v squared, which is going to be e to the 3x all squared. Like so. And that's a case of simplifying if we can do. So next line, we have e to the 3x on the top and e to the 3x squared on the bottom. So what I'm going to suggest we do, just for efficiency, is be thinking of this. E to the 3x squared is actually e to the 6x. Okay? The effect of dividing the top all by e to the 6x is these e to the 3x's will cancel. And if we remember, going back to GCSE and the laws of indices, e to the 3x all over e to the 6x, 3x minus 6x is e to the minus 3x, but we can call that 1 over e to the 3x. So essentially, these e to the 3x's will cancel, and on the bottom, instead of e to the 3x squared, we'll just be left with e to the 3x. For top here, if this cancels, we just have minus sine x. And this one here, we're going to have minus cosine of x multiplied by 3, which is obviously just minus 3 cos x. And then we can say this is going to equal 0 at w. So how can this equal 0? Well, for a fraction to equal 0, therefore the numerator must equal 0. So therefore we set minus sine x minus 3 cos x to be equal to 0. So minus sine x minus 3 cos x equals 0. We can now rearrange this and solve without too much difficulty. What I'd suggest here, though, is sines and coses mixed. What relates sine and cos? Well, that's going to give us tan. So what I'm going to do here is suggest that we divide both sides by cosine x. So if we divide by cos x on the right and the left, then what we'll get over here, minus sine divided by cos, that's minus tan x. Cos divided by cos is 1, so minus 10x minus 3 is 0. Rearranging tan x equals minus 3. So therefore the principal value, x, will be arctan, or tan minus 1 if you really want to, minus 3. We want this to 3 significant figures, so let's see what this gives us. So shift tan minus 3, we get minus 1.24. I'm going to give it 90 for now. In fact, no, I'll leave the calculator to do the hard rounding work. The x-coordinate, therefore, is minus 1.24. So that's, of course, going to be in radians. Pi over 2, we can just check this if we want to. So is this in range? I can go down to minus pi over 2, as low as that. So pi divided by 2 is obviously going to be 1.57. So if we can go as low as minus 1.57, this is not that low. So this is in the valid range. From minus pi over 2 up to pi over 2, the interval here is pi. The period of the graph of y equals tan x is pi itself. So this plus pi will already be out of the range. In any multiple of pi in an interval, if it's the graph of tan x, there'll only be one solution per multiple of pi. So that's the only valid value of x. So we've got the x-coordinate, is what I'm trying to say. Now we've got the x-coordinate, we can simply substitute in what y is. So therefore, in fact I'll leave it on the same screen. Apologies for the shoddy ordering. So therefore y will be cos of minus 1.24 all over e to the power 3 times minus 1.24. So rather than just typing that in and rounding it, we can use the calculator to actually remember the previously stored answer. So if I toggle back, that's my stored answer. So I now need to just to work out the corresponding value of y. I'm just going to simply type in the fraction button, cosine of my stored answer, divided by e, so alpha and then e, to the power of 3 times x, which is 3 multiplied by my previous answer, equals, I then get 13.4, again to 3 significant figures. So 13.4 is a corresponding value of y. So therefore, w is minus 1.24, 13.4. So clearly that's a slightly trickier example, but following it through step by step, it's not so bad after all. Work example 3 is a bit more involved. Let's have a look at this one carefully. Number 3, given that y equals 5x cubed sine x all over 3x minus 1 squared, use the chain and product and quotient rules to show that dy by dx is this absolutely awful thing here, which I'm not going to even repeat. So this is a question I've made up myself, just as almost like an extension. I've given you something nasty just to prepare you for potentially nasty questions you might encounter on your A-level paper. As I said before, usually in the A-level they'll give you the form they want it in, so don't worry about the form. Like I've said here, I've given you what form we're aiming for. So let's just do this step by step, very slowly indeed. Don't be freaked out, I'll guide you through it. We've got this one before, but obviously this here is a nightmare to do. So what we need to do is actually differentiate the top using the product rule, because we've got a product of 5x cubed multiplied by sine x, and this bottom here we can use a chain rule for that one. So, thinking of this step by step, let's imagine we've got 2 different questions. So let's imagine we had a question, if y equals 5x cubed sine x, in other words this top one, how would we differentiate this if y equals this? So I could always just say, well, we've got y already, let's use this to be a. That tends to confuse people. Think of it in terms of y. So right now, just ignore this question temporarily. So if y were to be 5x cubed sine x, just wave goodbye to this, then we can use the product rule to do dy by dx. So dy by dx would be 5x cubed multiplied by the derivative of the second thing, which is cos x, plus the derivative of 5x cubed. So bring the power to the front, so 3 times 5 is 15, and then we're going to have x squared instead of the x cubed. So this goes as 15x squared. Leave the sin x as it is, so just leave that as sin x. So that's okay as it is, but what I'm going to suggest we do, just for ease, you can see here our target is to factorise out a 5x squared. So we can do this now. Both of these values here are a factor of 5, and we can take out an x squared. So I'm going to rewrite this as 5x squared, x multiplied by cosine of x, plus 3 lots of sine x. However, what now if a different y were to equal 3x minus 1 squared? Well, what we could do here is use the chain rule like the question's asking us. So now we can say let y, oops, just where to put it, let y equals 3x minus 1 squared equals u squared. So in other words, we're just letting u to be 3x minus 1. Then we'd have that dy by dx is dy by du, du by dx. Differentiating y with respect to u, if y is 3x minus 1 squared, which is u squared, differentiate u squared gives us 2u, and then du by dx, this is just simply 3. So then we have 6u, and then u is, of course, 3x minus 1. Leaving it factorised, we have 6 lots of 3x minus 1. So now we've got these different parts differentiated, we can now think about returning to the actual question at hand. So actually our y is this. So using the quotient rule, u is the top function, which of course was again quite complicated, and v at the bottom is the bottom function, which is 3x minus 1 all squared. So let's just write this in. So our actual u is 5x cubed sine x, which we called here, just cheating, y. We differentiate it though, and we've got that the derivative of 5x cubed sine x is 5x squared brackets x cos x plus 3 sine x. So actually, this is our u dashed. So we can use this one as well. So if u is 5x cubed plus sine x, we can fill in from using the product rule that u dashed is 5x squared x cos x plus 3 sine x. Now thinking about v. So v is 3x minus 1 all squared. And then down here, cheating, we called, well, let's pretend y is 3x minus 1 squared. Differentiating that, we'll end up with 6 lots of 3x minus 1. So v dashed is 6 lots of 3x minus 1. So in other words, if v is 3x minus 1 all squared, then u dashed is 6 lots of 3x minus 1 because, well, we proved it there. And the same way, u dashed was this 5x squared x cos x plus 3 sine x. So we're going to have quite an awkward lot of algebra to deal with, but we're going to aim for it to drop out like this. And we need to show it, so we can't just say, yeah, it's this. So therefore, dy by dx, applying the quotient rule now, is v, which is 3x minus 1 squared. Let's put this all over a very, very big fraction because it's going to be very, very long indeed. So like I was saying, v, 3x minus 1 all squared. And then that's going to be multiplied by u dashed, which is 5x squared, brackets x cos x plus 3 sine x, minus what u is, so u is 5x cubed sine x, multiplied by v dashed, which is 6 times 3x minus 1. So it's colour coding it just for the hell of it really, because I like a bit of colour. So v u dashed minus u times v dashed, all over v squared. So v is 3x minus 1 squared, so 3x minus 1 squared squared is going to give us 3x minus 1 to the power 4. Now just take a look at the top and bottom of this fraction, numerator and denominator. We've got a common factor of 3x minus 1 on the top and the bottom. 3x minus 1 squared here, 3x minus 1 to the power there. So what we can do here is we can divide one lot of this. So if I just call this a 3, basically divide by one lot of 3x minus 1, this squared will become power 1. 3x minus 1 divided by itself, that will just completely cancel off. And so next we're going to have something a bit simpler on our next line. So now we're going to have 5x squared here. Let's do the fraction line first, actually. There we go. So 5x squared multiplied by one lot of 3x minus 1 multiplied by x cos x plus 3 sin x then over here minus 5 times 6 we can just replace with minus 30 if we wanted, but again because we want to leave it in terms of 5x squared, what I'm going to do here is just factorize out a 5x squared from this. So I've got minus 5x squared, extend this fraction line slightly, and then in brackets I'm just going to put 6 the other x sine x. All over now is going to be 3x minus 1 cubed. So next what we need to do is a few extra bits in fact, so we're not home and dry quite yet. What I'm going to suggest we do is expand out this thing here. As you can see we've got 5x squared in both pieces, so I'm going to leave 5x squared on the outside, and then let's think about how we're going to expand this. So this goes back to GCSE really, albeit with much uglier looking terms. You can use FOIL or the grid method. I'm not going to recap this at this stage, but I'm hoping you'll get what I'm going to show you get here. So 3x times x cos x, that gives us one term of 3x squared cosine x. Then multiplying the 3x by the 3 sin x, that'll give us 9x sin x. Then minus 1 times x cosine x is just minus x cos x. Then minus 1 multiplied by the 3 sin x is going to give us minus 3 sin x. And finally, having factorized out this 5x squared, we've got minus 6x sin x at the end. All over 3x minus 1 cubed. We can now simplify this down just by comparing like terms. So 3x squared cos x, we have this here, big tick. We're wanting to have 3x sin x as well, so the x sin x terms. So we've got 9 sin x over here, 9x sin x minus 6x sin x, that checks out. I need a minus x cosine x. We've got that, that's great. And finally, minus 3 sin x, we have that piece too, fab, and the denominator is fine as well. So now we can just do the final line, grouping together all the like terms, and then we've proved what we needed. So therefore, final step, this is going to equal 5x squared on the top. And then we want to say it's 3x squared cos x, 9x sin x minus 6 sin x, of course gives us the 3x sin x we require. Then we've got minus x cos x. Finally, minus 3 sin x like we had here. All over 3x minus 1 cubed. Quite a beast of a question. I did it deliberately. Please forgive me. But I'm hoping by showing you horrible questions in advance, it's better showing you them here than you being nastily surprised in an exam situation. So that's enough from me. Now it's over to you folks. So here's what I'd suggest you try. Turn to page 244, exercise 9e in the year 13 Blue Book. Try questions 1, 2 and 4, then the exam type, problem solving questions, questions 6 through to question 12. As ever, please do comment on the video if you're stuck or struggling, or ask me in person, or even email me. One way or another, please do ask for help, because this is a massive topic and it's not going to go away if you don't actually learn it. So thank you very much for listening. I hope it's been useful, and as ever, take care and I'll see you all soon. From me, goodbye from now.